Good afternoon, everyone. My name's Geraint Wiggins. I'm only going to speak very briefly, just long enough to introduce our speaker today, Anastasia Kruglova, who is doing her PhD at KU Leuven. Anastasia used to work in my lab on her master's project, which is how I know her. She did some really excellent work then, and I'm looking forward very much to hearing about her work today. I won't bother reading the title, you can read it yourselves, and she will explain it. Anastasia, the floor is yours.
Thank you very much. Thank you for the opportunity to speak here at the VUB seminar. So as Geraint introduced, I did my master's thesis at the VUB, and now I'm at the Gonsalves lab in KU Leuven doing work on more computational neuroscience. And the talk of today will be a joint of introduction to some neuroscience and then mainly on the contribution that I did to computer science. So the talk will be split into four main parts. I will first give an example of a mechanistic model about associative learning. And then I will introduce a package that we are developing to infer the parameters of these mechanistic models. However, inferring these parameters requires quite a lot of compute, and there are technical limitations to it. So I proposed a method called multifidelity simulation-based inference, and this will be, like, I think, 50% of the talk. So let's get started and give an introduction about associative short-term learning. So learning in itself has been described as some temporary modification of neural activity based on associations between stimuli. And for example, in humans, we are naturally attracted to chocolate, but if someone would give us chocolate made out of plastic and we are fooled, then we will associate this with some form of starvation, and we won't be attracted as fast to the chocolate. So I don't want to compare ourselves to worms, but they have very similar behavior. They are naturally attracted to salt, since they associate the presence of salt with the presence of bacteria that they are eating. However, when you give them a lot of salt without the presence of any bacteria, they start avoiding it. And the assumption in the field is that they learn some form of associative learning to not be attracted to salt for a short period of time of 15 to 30 minutes. And so why is it interesting to study the C. elegans? Well, they only have 302 neurons, and compared to the human brain, it is very interesting and I wouldn't say a simple organism because biology is very complicated, but way more interpretable. And there are also maps, so-called connectomes, that describe how the neurons are connected with each other, so-called synaptic connectomes. Even more, very recent work of our collaborators has described a neuropeptidergic connectome, and this is a connectome of, so we can call it Wi-Fi connections between the neurons. So what do I mean with this? Our neurons are connected to each other through synapses, which can be gap junctions or chemical synapses, and this signal propagation is the one that people are mostly looking at. However, the neurons themselves, they also eject some neuropeptides which diffuse on a much further scale and can reach neurons that are far away than the neighboring neurons themselves. And why is it interesting to look at these neuropeptides? Well, in the C. elegans, they saw that knocking out these neuropeptides resulted in behavior of the C. elegans not able to learn this aversion to salt at all. And in people, the lack of these neuropeptides has also been shown to be related to a few neurodegenerative diseases, such as Alzheimer's and so on. So our main question that we want to solve in my PhD project is to understand what the influences of this neuropeptidergic modulation on learning in the C. elegans during this salt-attractive behavioral task. And for this, we can create a mechanistic model that would use the connectome of the synapses and the connectome of the neuropeptides and join them together. And we can describe this network with some form of a differential equation where we have three parameters. And it doesn't really matter so much to understand what this equation exactly means, but imagine that we have some time constants or Earthing action potentials that can vary depending on how the C. elegans learns certain behavior. And so this neural network can be trained if we give the input the salt concentration that the C. elegans can train, and as output we know how the C. elegans behaves itself, then we can try to fit this neural network to the behavior. And so once this network is fitted, we can then read out the neural activity of the artificial neural networks created with this mechanistic model and compare this to neural activity of the biological system itself and make assumptions or predictions about the underlying mechanisms of the neurons and try to get more insights of what are the rules underlying neural connections. So here, I just want to emphasize that this is fundamentally different than what are artificial neural networks used in statistics and machine learning. So these mechanistic models, they are based on parameters that have some real biological meaning or interpretation. However, since it's a set of differential equations, they are quite hard to fit to data. And on the other side, you have the statistical models, which are very simple to fit to data, but the parameters themselves typically don't have a direct biological interpretation. So our question is, how can we fit these mechanistic models to data? And we can use a bunch of bachelor students and ask them to, okay, maybe this is a bit too cruel, to slide and search for the best parameters, but obviously this doesn't scale very well, especially if you have many parameters. Also, biological systems themselves are stochastic. If you would measure a neuron multiple times, you will get every time a different result. So you want to incorporate this probability or uncertainty in your mechanistic model itself and also in the inference of the parameters. So how do you go about this? Well, we have to solve the inverse problem. We want, given some real experimental data, we want to infer what the parameters are underlying the mechanistic model. And typically, we can only simulate from simulators, make forward simulations. And to get this inverse problem, to get this inverse result, we have to make use of Bayesian inference. So you probably have seen this equation millions of times, but let me walk over it just to give it in the context that we are using it. So we have the prior distribution over the parameter space, which can be defined as a uniform distribution between certain ranges. And this can be your prior belief about the parameter values between which ranges they are laying. For instance, that certain parameters cannot be below 0. Then we have the likelihood function, which describes how likely the observations x are under a certain parameter configuration theta. And to give a practical example, we have a simulator with these parameters that you can choose yourself. And if you have a certain configuration, you can get a bunch of different simulated data, since it's a stochastic simulator. And from this, you can then get some summary statistics of the traces. For instance, how many spikes did I get from my time series? And then finally, we get the inverse. So given some experimental data, we want to get a posterior distribution over the parameters. But how exactly do we get this? Because what I didn't mention is normally in Bayesian inference, you have this very expensive evidence, which is hard to compute. And this is where a lot of Bayesian inference methods are trying to improve. You probably have heard about Monte Carlo sampling and Hamiltonian Monte Carlo and so on. But here we actually have an additional problem because our likelihood is intractable. And what do I mean by this? So we can generate our data, but we don't have an explicit function of the likelihood itself. So how do we go about that? Well, there's actually a whole branch called simulation-based inference. In the past, it was called likelihood-free inference that tries to deal with this problem. And in the past, people started using sampling-based approaches such as approximate Bayesian computation, ABC, and then made some improvements on it. But the problem is that these methods were not very scalable. From the moment that you had many high-dimensional parameter spaces, they just were not able at all to get some sensical posterior distributions. And that's why quite recently people started using machine learning approaches and methods such as neural posterior estimation, neural likelihood estimations came up. And the power of this neural posterior estimation especially is that we can directly estimate the posterior distribution without even having to estimate this expensive evidence directly. So how does this exactly work? We use neural density estimators, more concretely conditional density estimators, with an underlying structure of normalizing flows, which you might maybe have heard before. And the idea behind this is that you have some distribution that you then, with a series of transformations, transform to a new distribution. And the power of this neural network is that it can also compute the inverse of the transformations. And when we estimate the neural likelihoods, we have a loss function that tries to minimize the distribution over x given theta. And what we do with neural posterior estimation is a simple trick of inversing this. And it tries to find the relationship between the parameters and the data that you are feeding in. So I'm part of a community that has built a whole package called simulation-based inference. And here's also a QR code to the package. And we are actually going next week to Germany to contribute and build further on it. And this is a summary of how it exactly works. So as I said, you have some mechanistic model, which is more or less the same as a simulator, and some prior belief about the parameters, from which you can simulate many data. This you feed to a neural density estimator. And now, given some experimental read data, you can now get a posterior distribution and propose consistent samples that have a high likelihood or probability to the data. However, this method has some limitations. From the moment that you have very complicated and simulators with very high dimensional spaces, parameters, it becomes hard to fit them. And my goal was this year to create a method that would be able to scale a simulation-based inference to these more complicated models. And as an example, I showed here this network model where we don't only want to fit just the synaptic connections between the neurons, but also the slow diffusion of these neuropeptides, with which many more parameters come into play. So I quickly will introduce the idea behind multifidelity. So imagine there is a comet falling on the ground, and we are all now NASA developers, NASA engineers, and you have to find a model within one day that will say what the velocity will be of the comet when it crashes on the ground. And you can go very quickly about this and say, okay, let's develop a model and assume that there is no air resistance at all between us and the comet. And so then it's very simple. We have our equation, and the free parameter, the acceleration, is already known, since this is 9.81 that you probably have heard and seen in physics before. And if we would be on the moon, this would be another number, but we don't have to infer anything at all. Obviously, this will not give a very good prediction about the velocity of the comet. So we can go middle fidelity and say, okay, let's assume that there is some air resistance, and we want to infer now the weights and the drag forces of the comet on the Earth. And this is becomes a more complicated problem. We can even assume that during the time that the comet is falling down, the morphology is changing, and we have some drag coefficient that is changing over time. So my question is to you now, which model would you use if I would say to you that we only have one day left? Let's actually vote. So who would choose for the first model? You can put your hands up. Okay, one person. Who would choose the second one? Who would choose the third one? Okay, 2 people. What if I say to you that we can get the accuracy of the last model using the first model? That's a big statement, I know. But so our assumption was that there must be some implicit relation between the parameter spaces of these different models since they try to solve the same problem. Using many simulations from a low-fidelity model can help us in some sense to estimate the probability density over the parameters of a high-fidelity model. And this would lower the cost of simulating and increase the accuracy. And more specifically, with what we came up is the following. So transfer learning has been used to pre-train on many simulations, and then you can refine it in a certain direction that is beneficial for you. And so what we decided is to use a low-fidelity model, to use a neural network, pre-train it on low-fidelity samples, and then use way less simulations to train a high-fidelity simulator. And then secondly, we can go even further, and now that we have our high-fidelity model, we want to give a few more simulations that are the most informative to us. And for this, we use an acquisition function that calculates the largest variance between multiple posterior estimators, and we try to sample from the regions where the estimators are the most different. So from these regions, we will get the most information out. And so the method, here is an overview of it. We have our low fidelity simulator that we train with our pre-trained model and do transfer on it in a new high fidelity simulator. And now we use these high fidelity simulations to get more accurate predictions. And this can be refined through this acquisition function. So does this work? Let's try it out on 3 different tasks. So the first will be a statistical benchmarking task, and then we will try it out on 2 computational neuroscience questions, from which the last one is a real big problem, and we were wondering whether our methods would be able to help and push the field forward. So the first statistical task is on the Ornstein-Ulbeck process, and this is a difficult name for a very simple process. So imagine we have a particle that has some velocity going to a certain mean, and it is a stochastic process. So we have here 3 parameters. We have the gamma, the speed of convergence, to a certain mean, and it has some standard deviation. And like the differential equation consists out of a drift and a diffusion part. And we can approximate this very roughly with time-independent Gaussian samples. So I know that we are not taking any knowledge about the time at all, but that's the idea. We want to have a very rough estimator of it. And since this problem has an analytical solution for both the high-fidelity and low-fidelity model, we can compare our predictions to this analytical solution and give a very good estimate of are we improving our method and getting better predictions or not. So this is what we got. We are evaluating it with a classifier to sample test, which is basically a classifier that is being trained on understanding how different the 2 distributions are. And if the predictions are close to 0.5, then it means that the 2 distributions are very close to each other. So our estimates are very good. And from the moment that it's close to 1, then it means that the 2 distributions are different. And so we compare it every time to the ground truth. And so you see, obviously, the more samples, high-fidelity samples we use, so you see there in 100K, the better the predictions are. But we want to use a very low number and pre-train it on like low-fidelity samples. And you see a very nice gradual improvement. So the more samples we used to pre-train the model on low-fidelity samples, the better it got. And refining with this acquisition function also made better predictions for the posterior estimate. And so then we decided to do this on a real-world task of a multi-compartmental neuron model. So in neuroscience, we can define a neuron as just a point neuron, where this is one simple Hodgkin-Huxley equation that doesn't change. But we can also define all the separate dendrites that have different compartments. And so we call this a multi-compartmental neuron. And since underlying there is a cable equation that we are separating different parts, we have a more accurate prediction and view on how the neuron itself is propagating the signal. And just to show an example, you see here the raw data of a low-fidelity model and a high-fidelity model. And you see that the neural activity coming out of this model is significantly different. And this is just about the accuracy of the model itself. And so we want to fit the parameters of them, which are ion channel gatings, and doesn't really matter so much what it exactly means, but they are some biological parameters in which we are typically very interested in. And so here the results were very fascinating. So we were evaluating it on a method called, with average negative log likelihood over 3 parameters. So you can mathematically show that if you go to infinity on these 3 parameters, this is a very good estimate of how your neural density estimator is predicting given some experimental data. And we saw that we could lower on the order of 2 magnitudes the required high-fidelity samples to make as good predictions as before. And just maybe to explain the legend, so you see NPE, which is this neural posterior estimation that has been used in the field for a very long time. And this multifidelity NPE is the method that we proposed. And the different numbers mean on how many samples it was pre-trained, so on 10 to the 3rd, 10 to the 4th, or 10 to the 5th low-fidelity samples. And then finally, we tried this out on understanding the plasticity rules in recurrent spiking neural networks. And so imagine that we have a network of more than 5,000 neurons, and some of them are excitatory, and some of them are inhibitory. And you can simulate them with very complicated differential equations, from which this is only like a small part of it. And so you try to, per neuron, see what inhibition and exhibition is with this GABA and AMPA and so on. And to simulate this, you need very heavy C++ simulations, from which just one simulation takes at least 5 minutes. And yes, you can parallelize all of them, but still it takes a lot of time to simulate them. And the longer your recording of this model, obviously the more expensive it gets. On the other side, there is also a mean field model that just assumes that we have one average excitatory neuron and one average inhibitory neuron. And they have a connection going from the excitatory to the inhibitory, and they have also some internal connection from excitatory to excitatory. And we can use this as an assumption where we have a much lower dimensional parameter space, and simulating this guy only takes, it's just instantaneous compared to a full simulation of this gigantic neural network. Since, as you see underneath, it are just 2 linear equations that we are using for that. So here we saw that even in this model, it already helped us in lowering the number of simulations we are needing. So by just training on high-fidelity samples, we were getting many samples that were outside the biological ranges of 1 to 50 hertz. And pre-training the model on this very rough estimate made sure that most of the predictions were inside the biological plausible boundaries. So as a summary, I presented to you simulation-based inference, which allows to infer the parameters of simulators given a simulator, prior ranges, and some experimental data to which you want to adjust the parameters. And so I proposed a multi-fidelity simulation-based inference approach that combines low-fidelity and high-fidelity models and different priors together to infer these parameter ranges for high-fidelity models. And so we saw that now we can push the boundaries of simulation-based inference further and scale it to more expensive simulators. And now my next task would be to try it out on this very expensive neural network, where we try to capture also the neuropathy connections between the neurons and see whether this would scale and infer some biological plausible rules behind learning and associative short-term learning. So with that, I would like to thank my lab, supervised by Pedro Gonçalves, and our amazing people, Zina, Michael, Najla, Meral, Hayden, and Kartik. And end with a multi-fidelity quote that I invented myself. It's a multi-fidelity quote of George Orwell and George Box. All models are wrong, but some are more wrong than others. Thank you very much.
Thank you very much, Anastasia. So, do we have questions? I think you'll need to wait for me to bring the microphone to you. Questions?
Thank you for your talk. Just a question. So you trained on the low fidelity model, and then you transfer learning on the high fidelity model. I saw in one of the slides you added one layer at the end of the network. Yeah. Did you just add one layer, or is it more layers? How does it influence the training, the transfer learning?
That's actually an interesting question. So at first, I was thinking that we should modify the last layer since the problem is slightly changing. What we saw is that we can see transfer learning more as a pre-configuration of the weights, and adding this additional layer was actually biasing the network more than giving more benefits. So by initializing the weights with a slow fidelity model and just retraining it gave the best performance. I think because they are trying to solve the same problem in some sense, and the weights are like already like going in the right direction, and this was just fine-tuning more in the right way. Mm-hmm.
Okay, thank you for a very nice talk. The ideas are very attractive and sort of make a lot of sense. Would you be able to somehow characterize the range of problems where this approach works and the limits of it?
The multi-fidelity approach, you mean?
Yep.
So actually, it's very redundant in science that you have different models for the same system. I just gave the problem of physics, but this can be like with Navier strokes, or in neuroscience, what they often do is, for instance, assume that there is just some Gaussian noise in the recordings. But what you can also do is to calculate, like, you see the membrane of the neurons, and you can simulate like all the ion channel kinetics going up and down, and use this as a more sophisticated stochastic process than just a Gaussian noise. And in this way, you can like build more and more and more complicated models. And like in theory, like all models have many assumptions. And just depending on for what we use it, we typically go for simpler or more detailed models. So almost for any problem, there are many ranges of fidelities for models. Yeah.
Okay, thanks.
Hello. Thank you for your presentation. Great. It was great. I have too many things to ask, but so I see a lot of connections with curriculum learning, spiking neural networks, even feature extraction, maybe, or feature selection more. So my question will be more about this last one, is like, so how do you choose the low fidelity and high fidelity models? Is that something you can make automatic in a way? Can you select, like, for example, okay, we have these assumptions. Can we kind of, having a high fidelity, can we create a low fidelity automatically?
Okay, so there is actually a very large domain of different types of low and high fidelity models that you can create. And so one way is knowledge from the domain. An expert will know what the simplification is from a high fidelity model to a low fidelity model. What people are also sometimes using are surrogate models, which are more data driven. Yeah, like we are preferring obviously mechanistic models since they're more interpretable, but there are many ways to go about this. And it really depends on the problem, I feel, and what do you want to achieve, yeah.
Thanks for the talk. You mentioned you use an acquisition function based on uncertainty to determine your next sample from the simulator. How do you quantify this uncertainty?
Okay, so wait, I can show you here. So what we do, we train an ensemble of posterior estimators, and especially in the low data ranges, they will have a lot of different predictions, right? And then what we look at is where are the predictions the most different between the posterior estimates, and then we sample actually from the regions where the networks dissonate the most.
Okay, I see. And is the influence of the ensemble size significant? Like, how big does your ensemble need to be to offer like a very insightful acquisition?
Okay, so here you have a trade-off between like how many networks you train, and you also want to lower the computational cost. So we fixed on 5 ensembles, and this was giving good results. So obviously we can like delve deeper into it and try to understand a function between how many ensembles you need, but this goes a bit beyond the scope and the idea that we try to solve.
Okay, cool.
Yeah.
Thanks.
Any other questions? Okay, so I think we've had a good question session there. After this, colleagues, Anastasia and I and probably other members of our group are going along to the QL, the Quartier Latin, just on the corner across the road, to carry on our discussion in a more informal context. If anyone would like to join us, you're very welcome to do so. Thank you very much for your talk, Anastasia. Please, another round of applause.